Se abre el departamento de electroquímica y electrocatálisis en este instituto, en el Leibniz Institute of Catalysis, y es actualmente el jefe, el líder de este grupo de investigación. Ha sido editor invitado en varias revistas científicas y además ha sido miembro de las divisiones de Electrochemical Society, Orgánica Biológica, de la International Society of Electrochemistry, y es miembro también de la Sociedad Química Alemana, en la parte de la división de electroquímica, en la Sociedad de Catalítica Alemania y en varias otras sociedades. Sus líneas de investigación principales son electrocatálisis, electroquímica orgánica, conversión electroquímica de moléculas pequeñas, CO2, nitrógeno, sistemas electrolíticos multifuncionales y recientemente incursionando en el área de la fotocatálisis acoplada con electroquímica. Bueno, sin más preámbulo, con ustedes el profesor Robert Francke. Adelante, Robert.
Muchas gracias. So thank you very much, Bernardo, for this very kind introduction, and also for organizing a very nice and fruitful stay here in Mexico. So I had a chance already to give seminars and talks at various institutions and to interact with scientists and students, and I hope that this will be a start of a very good and fruitful collaboration in the future with Mexican institutions in Rostock and Leibniz Institute for Catalysis. So thanks again, and let's start. So let's start with the presentation. So I will, in the next about 45 minutes, I will focus on different ways, different types of combination between catalysis and electrosynthesis, and I will show you how we can create synergies and make the synthesis of organic molecules more efficient compared to direct processes, uncatalyzed processes. So before we start, I actually would like to give a brief introduction on the topic. So for those of you in the audience who are not familiar with organic electrochemistry, and I think there are quite a few people here who are not in the field. So what we generally do is we take an electrochemical cell. It might look like this, a two electrode arrangement. We immerse two electrodes, we apply electric current, and we generate reactive intermediates. So at this, with a heterogeneous electron transfer between the electrode and the starting material. So we have an electrochemical step coupled to chemical follow-up steps to generate the desired product. So what we have to know a little bit is the organic chemistry of reactive intermediates, radical chemistry, polar mechanisms, but also the nature of the heterogeneous electron transfer and the way we can characterize it. So what I would like to highlight here is that catalysis can be used both to facilitate, to enhance these heterogeneous steps and also the chemical follow-up steps. So some of the advantages, maybe some people have learned already also during the course, that we have quite good reasons to carry out electrosynthesis. One of that is we can use electric current directly, perhaps from renewable resources, generated by wind or solar power, and we can directly convert it to chemical energy. And this is a traceless and inexpensive reagent compared to redox reagents. The electrode potential can be varied continuously, and this is another advantage. So we can adapt it to a certain compound and solution. We can address compounds with dialed in their redox potential simply by choosing the appropriate value, by choosing the appropriate working electrode potential. The energy input is quite selective, and in optimized electrolyzers we can obtain up to 85% or sometimes even more percent energy efficiency. And last but not least, so it's mild and safe. Mild because we operate usually at room temperature, and safe because we can generate highly toxic or highly reactive intermediates in situ in a very controlled fashion. What I would like to talk about today is rather are these aspects here. So the disadvantages or the challenges of the technology. One of that is the kinetic inhibition of the electron transfer. The kinetic inhibition, so the electron transfer comes with an activation barrier which has to be overcome. And for that we can use electrocatalysis, as all of you know. So this is also in electrosynthesis a very important field or subfield. And then there's an apparent restriction to oxidations and reductions. When we think of electrochemical reactions. We think of changing oxidation states, of converting or oxidizing or reducing functional groups, but I will show you also later on that we can catalyze or drive redox neutral reactions with the help of electrochemistry. And also an important topic is the supporting electrolyte. So when we think of sustainability, of making processes more sustainable, we have to be, let's say, true to ourselves, and we have to also take into account the salt, which has to be separated. And ideally, it can be reused, but nevertheless, it's going to be energy consumption, which we have to take into account. So recycling of supporting electrolytes. So this is another topic I would like to address today. Just something about the significance of organic electrosynthesis. So here we have the adiponitrile process. This is known for a very long time. It's a reductive coupling of acrylonitrile to make adiponitrile. The annual scale, production scale is 300,000 tons per year. It's a little bit declining lately because there's a process rising of hydrocyanation of butadiene. But nevertheless, this shows the power or the scale we can reach with this type of reaction or electrochemical reactions. This is a German process here. This is the so-called Lysmeral. This is a molecule which is used in soaps, fragrances, perfumes. And the first step is actually an anodic oxidation of a benzylic group. And this is also done with several thousand tons per year. So it's quite an important process too. And now this leads us to catalysis. The first challenge, let's say, the inhibition of the electron transfer, the activation barrier, and the overpotential, which we would like to overcome. And what is electrocatalysis from the point of view of an organic chemist? In this case, we use a chemical interaction between the electrode and the starting material in order to catalyze the electron transfer. So we can do this heterogeneously. We use an active electrode material where the starting material can adsorb. In the adsorbed state, we have the conversion to form the desired product. This is not what I'm going to focus on here today. What we often use in organic electrochemistry instead is a homogeneous redox couple, a redox couple which is interposed between the electrode and the starting material. So here we refer to this process as an indirect electrosynthesis, or we use redox mediators. So this is the same as electrocatalysts or homogeneous electrocatalysts. So I might use both of these terms throughout the talk, and I apologize for that. It's the same, It's in the end, homogeneous electrocatalysts and redox mediators. The advantage is that we can decrease the energy consumption, So by reducing the overpotential, we can improve or alter the selectivity. We can shape the course of the reaction. And then finally, we can also reduce the risk of electrode passivation. Disadvantage here are additional cost, and the workup is more complicated. This is also something I would like to show you how we can address that with our research, and hopefully also in future applications. So let's start with a redox couple or with a catalyst system which is well known already. This is the TEMPO. TEMPO is an N-oxyl radical, a stable N-oxyl radical, which can be oxidized at 0.3 volt versus silver nitrate to the corresponding oxoammonium species. And this oxoammonium species can react with alcohols. And this is the target conversion. We want to convert alcohols selectively to the corresponding carbonyl compound, a very important reaction. This is very important to highlight here. The potential of the alcohol is between 1.2 and 2.5 volt versus silver nitrate. So this depends a little bit on the moiety R. So especially aliphatic alcohols are very hard to convert. So they're cannot be converted in presence of, let's say, functional groups or not in, let's say, organic solvents, because the solvent would degrade in parallel. And then we have a formation of a transine intermediate. This will collapse and liberate the carbonyl species and hydroxylamine, and those together with a oxoammonium species, we can close the catalytic cycle in a comproportionation reaction. So again, I have to highlight, we can carry out the electrolysis at the potential of the mediator, not at the potential of the alcohol. And this is well known. This is well known since the 1980s, since the first publication by Semmelhack and co-workers, and it has been recently reviewed by Shannon Stahl in a Chemical Reviews article. So you find numerous applications. It's well known, it's stable. And so what we did, we used the system to show something else. So this leads us now to the separation process. The idea was to make mediators and supporting electrolytes which are enhanced in terms of size. So we wanted to create a size-exclusive process in order to ease the downstream processing. Yeah, so the idea was to make polymers with N-oxyl units and trialkyl ammonium salts, polymetacrylates, which are modified with these, let's say, functional groups. Yeah, to have a polymediator and a polyelectrolyte solution, yeah, to add a substrate to electrolyze. Yeah, and after the completed electrolysis, the idea is to use either ultrafiltration or dialysis to complete, yeah, to isolate the desired product. And this is a dialysis cell, a dead-end cell. So we add a small, let's say, mixture of small and large molecules. In this case, our electrolyte solution, and we separate our product, yeah, by pushing this solution through a size-exclusive membrane. It can look like this, like regenerated cellulose, yeah, and we can, yeah, adapt the pore size distribution to the molecular weight distribution of our polymers, and then we are able to retain the polymer and recycle it. So this was at least the idea at the time. This is my first PhD student, Benjamin Schiller. This is already several years ago. And he was really successful in that. Yeah? So he was able to develop a reaction. This is on a small scale in a divided cell. We use a size-exclusive membrane as a separator. Yeah? So in order to prevent the TEMPO species from, let's say, migrating to the cathode and being discharged there. Yeah? So as electric short circuit. Yeah? So we can use a divided cell here, a free electrode arrangement, and we can selectively convert or create these carbonyl compounds. Yeah? So these are allylic ones, aliphatic ones. Yeah? So a variety of different compounds. Using acetonitrile water as a mixture, water in order to, as a depolarizer in order to have hydrogen evolution as a cathodic half cell reaction. So proof of principle worked. Yeah? So it's quite selective, as you can see from the yields. Yeah? So the yields are quite good. Now it's of course important to demonstrate, yeah, that this is also recyclable, yeah, that we can reuse the electrolyzed solution multiple times. This is a recycling study. This has been done with dialysis. This is a very convenient separation technique because you simply put your electrolyte solution and your products or your product, let's say, post-electrolysis mixture into such a tube, into such a dialysis tube, and driven by the concentration gradient, the small molecules leave the dialysis tube, and you can simply wait. You have to be patient, but you don't have to do anything. Yeah, so that's a quite convenient way to make a product separation. Yeah? The other approach is shown here. This is a filtration cell from our laboratory. We apply 5 to 10 bar in order to enhance the separation. Yeah, so this is the faster process, but also less selective, as we can see here from the results. Yeah? But for dialysis, the performance is stable for at least 5 electrolyses. So this is the proof of principle, and we thought before we start with further developing a process, we want to, let's say, understand a little bit more what is going on the molecular level. Yeah? So we did some detailed analysis of the mechanisms which are involved and the processes. Starting with cyclic voltammetry. Yeah? So these are studies, this is work by Adrian Putlik and Nyara Molbati from my group. So here you see 3 voltammograms. All three of them are reversible. Yeah? So the green one corresponds to TEMPO, which we used as a reference compound, and the red one to acetoxytempo, which we used as a model for the TPMA. The TPMA is the TEMPO-modified polymetacrylate. Yeah? So those compounds are electronically very similar. Yeah? And this has a well-defined molecular weight distribution with 3.6 kilodalton as an average molecular weight. When we look at these CVs, this is quite interesting now. So they all look very similar. Yeah, first of all, so the appearance. Yeah, so it's a reversible redox couple. The peak current ratios calculated with the traditional Nicholson treatment here is 1. Yeah, so quite reversible. And what is important to mention, first of all, is that we have an anodic shift of those 2 species. Yeah, so anodic shift of the equilibrium potential of about 100 or a little bit more millivolt. And the second very important thing to mention here is the diffusion coefficient. Yeah, so what we see here are normalized currents, normalized versus the peak current. Yeah, and in fact, yeah, so if you look at the diffusion coefficients measured by voltammetry by varying the scan rate, we see that the diffusion coefficient for our polymer is much smaller. Yeah, compared to the small molecules. So we have apparently by increasing the molecular weight, a decrease in let's say the diffusion rate, the curbing of the diffusion. On the other hand, we have a higher oxidation potential, and this leads also to a higher driving force, yeah, which we will see on the next slide. We did some catalytic studies. Yeah, we repeated these scans in presence of these starting materials, you see the catalytic currents are plotted here in the middle, and at the bottom you see the rate constants, which can be extracted from the voltammetry under, let's say, kinetically controlled conditions. And we have to look at these catalytic currents and yeah, let's say vary the parameters in such a way that we can obtain, let's say, a kinetically controlled CV, and from that we can extract rate constants. This is a logarithmic scale. I want to highlight here that TPMA and isotoxic tempo are quite similar, yeah, in terms of rate constant. This is the homogeneous rate. It does not include the overall rate or the diffusion processes or let's say the overall current. Yeah, this is only referring here to the homogeneous rate. Yeah, so we can conclude now that the homogeneous rate is quite similar. Yeah, and it's influenced more by the, let's say, by the electronic properties of the polymer, and less by the steric hindrance of the polymer backbone. Yeah, this is and we are much better here compared to the standard tempo molecule. Yeah, so we have higher rate constants. The overall currents here are an interplay between diffusion, of course, the fusion of the polymer and of the homogeneous rate of the process, and as a result, we have a slightly decreased, let's say, current compared to the isotoxic compound. Yeah, so compared to this one. Okay, so in the next step, we were also interested in learning more about the influence of the molecular weight of the polymer. Yeah, so because we have seen in the first step with a single measurement, let's say, or with a single point measurement, that the polymer has an influence, has an impact on the overall rate of the process. So we synthesized by the raft polymerization technique, we synthesized 15 different samples, yeah, of the TPMA. We use also the dimer here as a model compound, this let's say malonic acid dimer, and also the isotoxic compound. Here you see the molecular weight distributions, let's say determined by GPC analysis. And here you can see how we analyze these processes. We do some analysis. We travel to the kinetic zone diagram in order to obtain these kinetically, let's say, controlled CVs. Yeah, so these S-shaped CVs. And here you see at a very high scan rate, yeah, you see that's sort of a convergence, yeah, a plateau formation. From these plateau currents, again, one can extract rate constants. In this case here, you see the plot of the maximum currents, which is a function here of the molecular weight. And yeah, this is shows us basically that we have to be careful with our molecular weight. We are not allowed to use, let's say, or not. It's not useful to have high molecular weights. Yeah, because the overall rate goes down. On the other hand, we have to keep in mind that the separation process requires larger polymers. So we have to find in the future, let's say, a good compromise, a good working range, or good let's say, sweet spot where we have a good, yeah, interplay or let's say a good compromise between mass transfer and rate of direction. Here, this is also, let's say, confirmed by controlled potential electrolysis. Yeah, so here we see the charge time profiles. Yeah, in the beginning here we have with isotoxic tempo a very fast conversion and a very slow conversion also with the larger polymer. Yeah. Okay, so this is a good, I would say, good demonstration of electrocatalysis. Yeah, where we use this chemical interaction in order to catalyze, let's say, heterogeneous electron transfer using a redox mediator. The precondition for such a process is actually that for an oxidation, that we have a mediator which is easier to oxidize than the starting material. Yeah, otherwise, we don't have an indirect or in-cell mediated process. If that is not the case, yeah, if this is not the case, we can still try to use this mediator in a different way. So if the reactive species, which we form by oxidation, is stable, yeah, then we can accumulate it and convert it with a substrate in a so-called X-cell mediated process. This is one example from our group, and this goes along again with supporting electrolyte concepts. This is the field of hypervalent iodine chemistry or electrochemistry for hypervalent iodine compounds. Those compounds are very useful in organic chemistry to make, let's say, a very interesting bond-forming reactions, rearrangements, cyclizations. Yeah, this is a reagent which, let's say, which is used, has been used thousands of times. Fills, let's say, books and chemical reviews articles. Yeah, so if we can manage to make these compounds electrochemically, yeah, so this could be quite an advantage. because the commercially available substances are toxic and expensive. It's better to make them in situ. That's what we have done here. So we generate as a 2-electron oxidation. We take iodoarenes, we oxidize them to the corresponding lambda-3 iodanes. And those lambda-3 iodanes can be converted in an XCell process in order to make a product. Let's say here this is an intramolecular cyclization to make carbazoles. We can also do an intermolecular dimerization here or coupling reaction to form this amide species. And we can also do cyclizations of these, let's say, iminophenols. What we also did here in this case is to introduce ionic tags to these molecules. This way we can, let's say, improve the separability. So we change the polarity of the molecule. On the other hand, we also don't need to add supporting electrolytes anymore. So this entire process becomes more sustainable. We have to, of course, recover the mediator, which is very easy by extraction, and the solvent has to be recovered. By the way, as solvent, we use hexafluoroisopropanol, which forms the dialkoxy lambda-3 iodine. This is the stabilizing X moiety here. Okay, so in this, let's say we finished this some time ago. We have made a proof of concept, but we also were interested in making hypervalent bromine compounds. Hypervalent bromine compounds are sort of a holy grail in organic chemistry, because they are more electrophilic. They have a higher oxidation potential, so they're stronger oxidants. On the other hand, they're harder to control. They're very hard to make because all the available syntheses are based here on this bromine trifluoride. This is a very nasty, let's say, a liquid precursor, which can only be handled with special equipment. So it's highly corrosive and requires PTFE equipment. So these are known processes, and we tried something, let's say, with electrochemistry here. So we take these bromoarene precursors. They can be oxidized. There's a 2-electron oxidation. Here are the optimized conditions, 4 Faraday per mole. And we can generate this in 63% isolated yield. So the key here is to have a stabilizing moiety in auto position. So what we do here in the end, we create a pincer, an OCO pincer complex of bromine-free. That's how the organometallic chemist would consider it. This is work by Igor Sokolov, a postdoc from Latvia in our group. So you can see the yields. We can also introduce various substituents. And the nice thing now is that we can, let's say, also alter the redox potential and alter and change the, let's say, the oxidizing capability of the reagent, of this XCell mediator. You can see we can also make it sort of predictable. We can plot the sigma p plus parameter, or the half peak potential versus the sigma p plus parameter. This is a Hammett correlation here. We see a nice correlation in theory. This would allow us to predict compounds which, the potentials of compounds which have not been synthesized yet. Here's something about application. When we made these compounds, actually, we were quite surprised because those are rather stable. So this is perhaps the first reported stable hypervalent bromine compound which can be isolated. And even when we tried to react with the starting materials, there was no reaction proceeding. So we had to activate it, actually. So we had to think about ways to activate this. So we can see this basically here as a compound where the intrinsic reactivity of the bromine-3 is locked. And this can be unlocked in presence of a Lewis or of a Brunstad acid. So, and then once this is done, we can convert this with a substrate to obtain the desired product. We've done this here with the anisole coupling. This is an oxidative anisole coupling to obtain the bisanisole. We can do this CHSP3 amidation of these aniline derivatives. It's phthalimides. And we can do also the good old cyclization of these iminophenols. So it's quite useful, this reagent. Of course, further studies are ongoing. These are only the first demonstrations. So having demonstrated the utility of this XCell mediator, we wanted also to learn more about the mechanism. So we did some cyclovoltammetry studies again. When you look at this compound, there is a irreversible redox couple here, a 2-electron process appearing at all scan rates, which we have tested. And this is different here for the paramethoxy substituted compound. This is quite interesting. We see when we increase the scan rate, or when we increase the scan rate, we see the appearance of a reversible redox couple. This is quite peculiar. And also when we look at the plot here versus the square root of the scan rate, there's linearity. On the other hand, we also see that apparently we deal here with a single electron transfer, with a 1-electron process, even though we observe in the electrolysis, in the controlled potential electrolysis, the formation of the bromine, yeah, of the bromine free species. A potential explanation is shown here. Yeah, this is cannot be seen here, but when we oxidize 2A, the non-substituted compound, the spin density and charge density is sitting mostly on the bromine, whereas here in this methoxy substituted compound, yeah, the spin density and charge is distributed across the ring. Yeah, so apparently there's some stabilization. So what is happening here? Yeah, we take our starting material, we oxidize, we form the cation radical. The cation radical now can be deprotonated. In most cases, the step is very fast. We form the radical. And this can be further oxidized and then deprotonated. And we have a classic, let's say, EC mechanism. If this deprotonation is slow, then this intermediate radical has time to diffuse into the solution where it is slowly deprotonated and then react in a comproportionation, yeah, to finish the reaction. Yeah. We can detect this also here with spectroelectrochemistry. So this cation radical is rather stable. Yeah, so we can really detect it with UV-vis spectroelectrochemistry. And yeah, so this was quite interesting just to figure out the mechanism of this. We were also interested in studying the reduction mechanism. So we did again here linear sweep tomograms. We can plot, we can make the Hammett treatment. This all works not so nicely. They don't behave so nicely reductively compared to oxidation processes, but nevertheless. And then this is also quite interesting when we reduce them electrochemically, these compounds, we can obtain the starting with so the bromorine in 74% yield, but this is a one electron process apparently according to coulometry. So what we do here in acetonitrile is we form the radical anion, and then this radical anion can do a hydrogen atom abstraction, yeah, from the solvent, yeah, in order to form the negatively charged species. And we can learn from that. Basically, this is very important to study this reduction process also electrochemically, because we can learn a little bit about behavior of this, yeah, of this substance and the behavior of the intermediates, because there are potential intermediates also in chemical oxidation processes. We also wanted to study the mechanism of some of these conversions in order to understand how our reagent acts. Yeah? Is it an outer sphere electron transfer mediator, or is it, let's say, is it undergoing polar mechanisms? So this we have done for all the examples so far. I just want to discuss briefly the conversion of these anilines. Yeah? So we think, according to our mechanistic studies, we think that we have a transient formation here of this of such an adduct, yeah, a Lewis base interaction, and let's say an intramolecular rearrangement, reductive elimination here, and then at the bromine center, which forms an iminium ion. Yeah, this iminium ion we think now reacts with the phthalimide substrate. This is also confirmed by computational studies here. So the creation of the iminium ion goes downhill. It's a friendly process. It's an energy or energetic, its favorite process here, whereas the formation of a radical ion pair is unfavored. This can also be, by the way, can be confirmed with a radical clock probe, which shows, yeah, that there's no radical present, yeah, during the reaction. All right, so now we have seen X-cell and in-cell mediation, right? The in-cell mediation was the process where the mediator is continuously regenerated during the electrolysis. Yeah, this was a tempo case. The second part, the hypervalent bromine and iodine compounds, these are so-called X-cell mediated processes. Yeah, so whenever the potential of the mediator does not match the potential of the substrate, yeah, then we can use X-cell processes. Now we have another way to let's say combine catalysis with electrosynthesis. And this leads us to the last chapter of this presentation. This is the so-called electrochemical catalysis. And in electrochemical catalysis, we do the opposite of electrocatalysis. So we use, instead of using a chemical interaction, yeah, to catalyze an electron transfer, we use an electron transfer to, let's say facilitate a redox neutral reaction. Yeah, so what we do, like this is shown in this general scheme, we use electrons and holes as catalysts. So let's assume a process A reacts to P, a thermal process, a redox neutral process. A has now also the chance to react at the electrode when we operate under electrochemical conditions. So let's assume that this is a thermal process which requires higher temperatures. And here we oxidize the substrate instead at low temperatures. We form the cation radical. The cation radical can now undergo a chemical reaction. It's sort of a relaxation process. This is like a favorable process. We form p cation radical. If this process is fast, then p cation radical is now capable of donating back its positive charge to the electrode. So then we finish the reaction. We have the desired product here, and this is a so-called ECEB mechanism, where the second electron transfer step is a backward electron transfer. If this process is rather slow, then the cation radical has time to diffuse into the solution. Then it can slowly react to p cation radical, and the p cation radical can now oxidize the starting material, and then it forms a chain process. In both cases, we only need catalytic amounts of charge. So this is ideally we don't observe any current at all. But the current we observe is usually due to a termination of the chain process. So the charge which flows is due to side reactions. So we can let's say define a new value or a new criterion for evaluation of the efficiency of the process, the so-called ton E, the number of conversions per passed electron, and the turnover number, which of course in a catalyzed process is higher than 1. Okay, so this is one example from our group. The Newman quarter rearrangement, the thermal rearrangement of OR-real thiocarbomates to the corresponding SR-real compounds. And this is a second step of the 3-step synthesis of thiophenols from the corresponding phenols. This is work by Aaron Drösel and Timo Bröse, by the way, you both graduated 2 years ago already. And so what we do, we introduce in the first step this auxiliary, and with this auxiliary, then the rearrangement can happen, usually under thermal conditions in this spirocyclic Zwitter-ionic transition state, which is an explanation for the high temperatures which are required, so between 200 and 300 degrees centigrade. And instead of using these harsh conditions, sometimes with electron-rich compounds, we even need almost 300 degrees centigrade, which decreases, of course, the selectivity of the process, causes side reactions. We try to do this at room temperature. So we use a galvanostatic electrolysis in an undivided cell. We apply catalytic amounts of charge, and the most important thing again, this is done at room temperature. And the key ingredient here is of course to add a salt and the hexafluoroisopropanol. I will comment on this hexafluoroisopropanol solvent later on. That's quite important. So here you see the product scope. We can make mostly electron-rich products. And keep in mind, compared to the process I've shown before, here we have a preferably conversion of electron-deficient compounds. Because here in this thermal rearrangement, we see that the negative charge is sitting on the aromatic ring. And when we have an electron-donating substituent, this will increase the activation barrier of this process. So it's the thermal reaction is, let's say, a good process for electron-deficient starting materials. And here we see the opposite. We have complementary reactivity regarding the arene substitution. Those are all very electron-rich substrates. Neutral ones can also be converted. We need slightly higher temperature, and the reaction doesn't work even at high temperatures for the electron-deficient compounds. So it's a quite useful and complementary approach for the classic rearrangement. We also studied the mechanism, and before we go to the mechanism, I would like to discuss a little bit the upscaling. So we have a batch electrolysis. This can be done in the regular batch type electrolysis cells. We can convert 2.1 gram of starting material, and with 99% yield, the turnover number is 11. The problem is now here. The problem is the salt. 3.4 gram of salt. It's not sustainable, let's say. This is in our lab. This is waste, and this is quite expensive. These tetrabutyl ammonium salts, which are needed for these organic electrosyntheses. What we do instead is we use a microflow reactor with very small inter-electrode distance, and this allows us to usually lower the supporting electrolyte load. In our case, it's even possible to make this under salt-free conditions. And our idea is, or the reason why this is possible, we think, is the generation of this cation radical chain process. So we, instead of quenching our charged species, which is formed at the electrode, we sustain a chain, which in the end is this entire mechanism is our supporting electrolyte. And this allows us to operate under salt-free conditions. So what we have to do, only after the electrolyte has passed the electrolysis cell, we have to evaporate our solvent, and we have the pure product in our hand. Okay, let's look at the mechanism of this, and we have discussed this a little bit in the electrocatalysis course on Sunday, and the students who attended this course are now well prepared to understand. And so what we do when we analyze these processes, we take the starting material and the product. Yeah, this can be prepared separately. We start with the starting material, the black curve. We see an oxidation. This corresponds to the formation of the cation radical. Then the current drops dramatically, actually. So we don't reach the fusion plateau, but we go even to negative currents during the anodic scan. And this is, of course, due to the triggering of the chemical process, which leads to the backward electron transfer. Yeah? So we can get even negative currents in the anodic scan. Yeah? And then, of course, when we form the product cation radical after reduction of the product cation radical, we have product which can be oxidized. Yeah, this is the second peak, and this can be confirmed when we compare this black voltammogram to the voltammogram of the product, yeah, which only has one peak, a single peak in the forward scan. It can be considered as a criterion, yeah, to study the feasibility of the rearrangement, yeah, but without even having to try the preparative scale electrolysis. And here's the other example, the parafluoro compound, where we know from preparative studies that NKR is not possible. And we see again this oxidation peak. So the oxidation of the starting material is not the problem. We form the cation radical, but it can now not rearrange. And we see another feature here which does not correspond to the oxidation of the product. Okay, I don't want to bore you with more CVs and more results here. I just want to highlight with this, let's say, concentration-dependent measurement that we can observe the chain mechanism. So here's the non-NKR case where the rearrangement is not possible. We see a regular Randall-Sevcik behavior and as a function of the concentration. This is the peak current as a function of the concentration. And for our rearrangement cases, we see that the currents are lower. They are smaller, and the faster the rate, the smaller the current is here. And this is the fast reaction, this is the slow reaction, and we see that the current drops even further. Yeah? So here in this case with electrochemical catalysis, we can conclude that the faster the chemical step is, the smaller the current. Yeah? So this is the contrast to electrocatalysis, where fast coupled chemical steps lead to high currents, the so-called catalytic current. Okay, so we wanted to know more about the mechanism here again. And we used cyclic voltammetry again as a tool to understand also the molecular rearrangement. Usually this is not possible. Usually we think that cyclic voltammetry is blind to structural features. But when we analyze a lot of data, in this case, we plot the half-peak potentials versus the sigma p plus parameter, again, a hammer treatment, we can say something about the localization of the charge and of the rearrangement mechanism. So in this case, we see there's no influence. This is the overall starting material and cation radical couple. Yeah, so we have no slope, almost no slope. The slope is 0, which tells us that there's no influence of the substituent here, and as a conclusion, we oxidize the carbomoyl moiety instead of the arene ring. When you look at the product couple here, yeah, we see that the cation radical is located mostly on the aromatic ring because there is a substituent influence. And as a consequence, we can conclude here that this is an electrophilic intramolecular aromatic substitution mechanism. And this is, I think, very important to understand how the process works. Yeah, these are results of a computational study with collaborators from Berlin University, Michael Römelt and Michael Gandhi. They compared the thermal process with the electrochemical process. So let's have a look at the thermal process first. Yeah, we we rearrange our product via this Zwitter ionic transition state, like it's proposed in the literature. So this is a process which requires about 50 kcal per mole, and this explains why the temperature has to be so high. Instead of undergoing this energy-intensive process, we can also now excite our starting material, using the terminology of photochemistry or photocatalysis, and we elevate now our starting material to a new landscape. This is a new energy landscape, the cation radical landscape, and in this landscape, the rearrangement barrier is much smaller. Yeah, so it's 10 kcal per mole, yeah, instead of 50 kcal per mole, and this explains why this reaction works at room temperature. And here, this is also the explanation why this is not shown here, the result, but this is also the confirmation of the role of hexafluoroisopropanol. Hexafluoroisopropanol is a hydrogen bond donating solvent, excuse me. And the stabilization or the hydrogen bond donation goes mostly to the oxygen, yeah, to the carbonyl group. And this has been confirmed with computational studies, including solvent molecules. Yeah. And this is the species which is stabilized the best. This increases this barrier or this gap, this energy gap, and this adds driving force to the chain mechanism. Yeah, so this makes the reaction faster. So recently we have also managed to overcome this problem with the solvent, because hexafluoroisopropanol is, whoever of you worked with that solvent, is quite expensive. And yeah, it's let's say also has some sustainability issues. It's not the most sustainable solvent in the end, and not the cheapest solvent. Yeah, so it's good to have an alternative which works with cheaper solvents. Yeah, and this is the photochemical version. Yeah, we can also, instead of using electrochemistry, using a photocatalyst, titanium dioxide particles, anatase, we can irradiate with 405 nanometer LEDs, and we can make the same cation radical rearrangement happen. And when we have to look at these results, those are yields. Here, this is the paramethoxy substituted compound, RS paramethoxy. And we see that we have to be a little bit more patient. Yeah? We can use another solvent, but we have to be more patient. Yeah? So 8 hours, I think, is still an acceptable time for the reaction. This works also for electron-rich compounds mostly. Yeah? So this is, again, a confirmation for this cation radical mechanism, but the mechanistic studies are still ongoing. These are very fresh results, are currently elaborated by Katrina, a PhD student from Latvia. Okay, for the sake of our schedule, I think I will skip the summary, and I think you have got the most important messages, the different ways we can combine catalysis with electrosynthesis in order to make these processes more efficient. Yeah? I would like to finish with thanking the group members, of course, the members who were involved in the studies I've shown directly on the slides. I would like to thank the collaborators. Yeah, I would like to thank for financial support. You again, Bernardo, for the invitation. I would like to thank also Erika Mendes for tremendous and very good organization of this conference. I'm really enjoying it so far and make very nice contacts, had very nice discussions. And of course, I would like to thank you, the audience, for listening, and I'm happy to take questions now.
Muchas gracias. Tenemos tiempo para unas preguntas breves. Por favor, ¿alguien? Nacho, por favor.
Very nice.
Nacho.
I enjoy it a lot. Another thing, one question. My main question in this kind of, particularly from the electrochemical catalysis, is the competition between the reaction layer and the diffusion layer. Because particularly, for example, for the electron transfer very fast, the chemical layer, the chemical reaction layer, grows very fast. In this way, how do you take in account this competition when you scale up this one? Because here the mass transfer and the modulation of the electrochemical process is very important. How do you take in account this from the scale up? This kind of synthesis.
So you're referring now to electrochemical catalysis, right? And you
yes.
have a very broad, yes.
Yes, because the reaction takes place in the surface or very near of the surface, but for the catalysis also, you need that the main A, for example, go to the surface. In this way, if the mass transfer is very important for make.
Yes, so for upscaling, I would say we can increase the flow rate or reduce the residency, yes. the residence time. I wouldn't do this in a batch cell, well, in this case we were quite lucky because we have a very favorable discharge process at the cathode. Yeah, we can normally, if we have an aprotic solvent, this would lead, what you suggested, this would lead to termination, right?
Yes.
Chain termination, which in the end is not bad, which would mean that we use stoichiometric amounts of charge. Yeah, so this would not lead to side products. Yes. But this would not be catalytic anymore, let's say. But if we want to maintain this catalytic process, and I would say, like you suggested, to push the solution through really fast. And this is what we have done in the microflow reactor.
One more question. In this
yeah.
relation, which is the parameters that you use for scale up this kind of the reactor? Because in the small cells, it's possible to control the diffusion, the current distribution on the electrode. But for the scale up, for the very big reactors for that, which is the parameters that you take in account from the scale up?
Yeah, of course, the electrode surface, yeah, increase the electrode surface, to increase the. this is a very difficult question because we're operating it on a very small scale. Yeah. I think this is a very interesting question. Maybe we can discuss later, I would say. Yeah. Yeah. Yes. Very important point.
Yeah, because in the course he showed the Lismeral process, which is large scale, and you have very thin separation between the anode and the cathode, and that's the circuit of this industrial process. I think that
this is an interesting point. So regarding energy consumption, yeah. So like keeping the cell voltage low. In our case, yeah, we have shown that we can even operate with half a centimeter interelectrode gaps without supporting electrolyte, because this chain process is so efficient. But of course, this will increase the cell voltage. I would say for this type of compound, the cell voltage is not so important because we have let's say highly valuable products, and we don't form them on a megaton scale, let's say. So we make kilograms or maybe a small in a lower ton area. And there I would say the energy consumption is not so much the key. Yeah, so the energy consumption becomes more important with cheaper molecules, let's say water oxidation or chloralkali electrolysis and so forth. Yeah.
Pasamos a otra pregunta, Mario, por favor. El micrófono. Y el siguiente micrófono acá con el doctor Norberto. ¿Sí? ¿También? Okay.
Beautiful work. Congratulations on the large scope and the amount of detail. So I have a couple of questions that I hope are quick. One, you had, I think, in one of your mechanisms, you had, I guess, an intermediate reacting with acetonitrile, and that struck me as odd because we normally think of a large, 5 volts or so potential window. It didn't strike me as obvious that it would react with acetonitrile. And then the second question is on your slopes for the mechanisms for the potential versus the Hammond plots type of stuff. You have slopes of 0.46 volts or so, but the scattering of the data, the error in that, and I thought in these systems IR drop will be a big issue. Could you comment on those?
On your second question, IR drop is compensated in all measurements. We do this all the time. The scattering comes not from the, let's say, accuracy of the determination of the potential. It's more, let's say, the parameters we use. Yeah, so they were determined for different systems. Right. Yeah, so, but still, I would say they well reflect the influence of the character of the substituents. Yeah? Right. So maybe qualitatively, at least, we can say that.
Sure. It's just that to what extent one could look at some of those and assign a mechanism, because that would be the most interesting part in my view, at least, right?
Yeah, I think qualitatively it's still a very good measure, or still a very good way to demonstrate the type of mechanism. On the other question, this was the influence of acetonitrile. Yes. It's indeed not the best solvent for H-atom abstraction, and it's electrochemically very stable. Yeah, but keep in mind that this is not an electron transfer reaction or outer sphere electron transfer. This is an H-atom abstraction. Right. So if you look in the literature, organic synthesis, it's compared to DMF maybe not as good for H-atom abstraction, but in our case it seems to work. It's the only explanation for one electron reduction. Yeah, and on top of that, we found some very old literature also from the Savillon group where similar, let's say, H-atom abstraction has been observed and proven experimentally. We didn't do any proof here with you could try, of course, with deuterated solvents or whatever, but okay, it's a good explanation, let's say. Yeah,
I wasn't aware of that, but thank you.
Yeah.
Gracias. Una última pregunta, porque ya nos tenemos que ir con el doctor Felipe González, y una cortísima con Norberto. ¿Sí? Vamos a ver, que me dijeron que ya vayamos cortando.
Well, thank you for your nice presentation. I would like to know what do you think about the shift of the formal potential of your polymediator? Because it seems that the electronic communication between each redox probe is not very well established. No?
Sorry, which mediator are you referring to? The bromine, the hypervalent bromine?
No. You show us a polymediator in which the redox probes are nitroxyl radicals. Yeah.
Tempo.
The tempo, yeah, the forward shift. This is Okay, so this has been reported already by Shannon Stahl, of course, not for our polymediators, but for the isotoxic tempo, and not isotoxic tempo, but for similar, let's say, tempo derivatives. This is the electronic influence of the substituent. I agree with you that the communication between the substituent and the N-oxyl moiety is not very strong, but still it seems to be enough to give us this additional shift or this additional driving force in order to increase the rate of the chemical step, yeah, of the catalytic step.
Okay.
But it's a really interesting question. Yeah. So far I discussed with many people about this, but the communication seems to be very low.
Yeah.
Maybe it's a through space communication. I'm not really not sure.
Yes, because when there is cases in which if the communication is not very strong, the oxidation potential is very close to that of the redox proof, the single redox proof, no?
Yes.
Thank you.
And a final question, Norberto? Sure. Because empezamos 10 minutos tarde. Okay. Well, he will ask you later.
Okay.
En nombre de la Sociedad Mexicana de Electroquímica, le doy una constancia al doctor Robert Francke por haber impartido la conferencia magistral y firman el doctor José Cabral, el presidente del comité ejecutivo, la doctora Erika Méndez Albores, presidente del comité organizador de este congreso, y a nombre de la rectora, la doctora Lilia Cedillo Ramírez, te entregamos un obsequio por tu participación. Muchas gracias, Robert.